Hello everyone. In this video, I'm going to show you how to use Matplotlib to create an animation. Now, animations are a very important part of coding in engineering and the sciences, and that's because they are very effective at conveying a lot of information, especially information that changes through time. So let's see some examples. Here are 4 examples of animations. On the top left, we have an animation of the trajectory of a drone, which is this green dot, as it follows a trajectory, which is the black line. On the top right, we have an animation of the 1D wave equation. Now, this is the partial differential equation that describes waves on a string that is pinned down at both sides. It begins with an initial condition, which is a plucking in the middle, and then waves go out to the sides, and then they come back, and then they coalesce again into that same plucking. Now, if there's dissipation, then those waves will eventually subside. But in this simulation, I have no dissipation, and so these waves would go on periodically, in theory, forever. On the bottom, we have simulations of the 2D wave equation. That is waves on a membrane, a square membrane. Again, there's an initial condition, which is sort of like a plucking. It'll come, there it is right now. You see it on the left as well. And on the left, we have the view from the top. And so here we can really appreciate the interference patterns that form when these waves sort of go through each other. So in this video, we're going to learn how to make these simulations and animations. We're going to use the 1D wave equation, the top right, as our example. We are going to follow the pattern of simulation code that we learned at the beginning of the module. And then the animation piece will be at the very end. So let's get started. Let's begin by understanding a little bit about the 1D wave equation. So in its most basic form, the 1D wave equation is a partial differential equation. Now, this not being a course on PDEs, we don't need to understand this in detail, but we do need to understand the notation. As I said before, the 1D wave equation describes the movement of waves or vibrations through a string. And in our case, that string is going to be pinned down at both sides. We're going to use x for the spatial dimension. So at one side, we have x is equal to 0. The other side, we have x is equal to capital L. And then we're going to use u for the displacement value. So u starts at 0, 0, and then it becomes positive here. And it goes back down to 0, then it becomes positive, and then it ends up at 0. So u is a function of x. But it is also a function of t, that is time. That's because it changes, it evolves through time. So we can imagine another dimension coming out of the page and call that t. And then we can imagine this shape morphing as it goes through time. Now, we see here the PDE, it says that the second derivative of this function u with respect to time must equal the second derivative of u with respect to x multiplied by a constant c. Now, this constant is the wave speed. That's the speed at which these waves are going to move. So this one is going to the right at a speed c meters per second, and this one's going to the left at a speed c meters per second. Here we see a 3D surface plot of the function u plotted over the tx plane. So here we can appreciate that the initial condition at time 0, so here's time 0, is this sort of plucking or impulse type function, and that after a few moments, say by time is equal to 0.6, now we have 2 waves, and they are moving away from each other at this velocity c. Now, our goal is going to be to compute this function u and to plot it and to make an animation. And we're going to do that by applying this initial condition and also applying these boundary conditions that say that at x is equal to 0 and x is equal to L, that the string is pinned down, so its displacement must be 0. So with those conditions given and the PDE acting everywhere in the interior of this domain, we can compute the solution U. To compute our solution, we are going to need to overlay the TX plane with a mesh or a grid of points. And to do that, we need to first discretize time and discretize space. So let's start with time. You remember that the time variable is lowercase t, and it goes from 0 to capital T. Now, we are going to split that interval with capital K nodes, which I'm drawing here. And so I have capital K of them. That's this symbol, capital K. And we're going to index those 0, 1, up to capital K minus 1. So the interval of time, 0 to t, is a subset of the real numbers, whereas these indexes are natural numbers. Now, the space between these nodes, we're going to call that delta t. And of course, we must have that delta t is equal to the uppercase T divided by the number of segments, k minus 1. So that determines delta t. Then if we take an arbitrary node, say this one, it has an index k, and it also has a time t. And those two are related with k delta t is equal to the time t. Now let's do space. So space, the symbol is x, and it goes from 0 to capital L. Again, we are going to split this into a number of grid points, and those grid points are going to be indexed from 0 to capital I minus 1. So we have capital I grid points on the spatial dimension. The distance between those is delta x, where delta x must be equal to L over I minus 1. And for any arbitrary grid point, we have that its x value is equal to its I value times delta x. That's this formula here. Now that we have a mesh, we can use it to go from the PDE to an update equation. So what do I mean by this? Well, the update equation is a formula that goes into our iteration over time and is used to compute U at a time k based on the U's at previous times. So to find that update equation, it's a mathematical operation that we're not interested in this course. Rather, I'm giving it to you right here. This is the update equation. Okay, let's see what it says. So the update equation says that the value of U at some time k and location I will depend on the U at the previous time and location I, on the U at the time 2 steps ago and I, and also at the on the U at time k minus 1 and I minus 1, k minus 1 and I, and k minus 1 and I plus 1. So on this graph, we see this green line is the U at k, red is 1 time step ago, and blue is 2 time steps ago. So U at k and I, so this is node I, this is U at k and I, depends on U at k minus 1 and I, that's this value, k minus 2 and I, that's this value, then k minus 1 and I minus 1, that's this value, the red one, and k minus 1 and I plus 1, that's this one. So this orange value depends on 4 previous values. Now you can see that this equation also involves this gamma parameter. And gamma depends on the wave speed c and also on delta x and delta t, that is the parameters of the mesh. And there's one requirement. Gamma must be less than 1. That's a numerical stability requirement. If it is violated, if we have gamma greater than 1, then as we move forward in the simulation, the solution can explode. So we just need to check that before we start our simulation. Before getting into the coding, I just want to describe the data structure that we're going to use to hold our solution. And that is this matrix or 2D array that we call U. And so U is going to have capital K rows, so that's the time dimension, and it's going to have capital I columns, that's the space dimension. So time is numbered 0, 1, 2, all the way down to K minus 1, and space is 0, 1, 2, all the way up to I minus 1. All right, so when we initialize this matrix, we are going to write the initial condition to the first row. And then in the iteration, we are going to fill in the rest of the rows. And the boundary condition will be imposed by writing zeros to the first and the last column. Then within the iteration, we are going to fill in the interior of this matrix with the results of the update equation. Okay, let's get to coding. So it begins with our standard imports, and then we define constants. We're going to define the wave speed to be 0.5 meters per second. We're going to simulate for 8 seconds. Then the length of the string will set to 1 meter. The time discretization is 0.01 seconds, and space is going to be chopped into pieces of 1 centimeter. Okay, dependent quantities. We need to calculate gamma, and that is equal to c times dx over dt. And we need to check that gamma should be less than 1. So I can say if gamma is less than 1, that's good. We can print good to go. And otherwise, we'll print gamma is too large. And let's run that, see what we get. I have to run the first things first. Okay, good to go. If we had gotten gammas too large, we would want to change the values of dt and dx until it complies with the requirement. Next thing that we want to do is compute our discretization. So t is going to be the grid of points that is going from 0 to capital T every dt. So let's run that. We get here from 0 every 0.01, but we see it goes up to 7.99 because a range is non-inclusive. So in order to comply with what I described before, which was going up to 8, I'm going to add a plus dt here. And now t indeed goes all the way up to 8. Okay, very good. Now we can define k as the length of this t, and we see that we have 801 grid points along the time dimension. Let's do the same for space. X is going to go from 0 to capital L every dx, and then I is going to be the length of x, and we have 101 grid points along the space dimension. Next, we can define auxiliary functions. We have none. Then memory allocation. Well, we need to allocate our matrix U. So I can say np.empty of size k rows and I columns. And so I have a matrix of size 801 rows by 101 columns. Now, I could have used zeros here. As I said, I like to use empty when I am promising that I will fill in every single element in the matrix. Next, initialization. Remember, we have to set the first row in U. And so U, the first row, every column is going to be equal to that initial condition, which is the plucking function. And we need that function. And I have it here. This is just the cheat sheet. This is the initial condition. It's actually a Gaussian function. And as you remember, the update equation, in the update equation, each k depends on 2 previous rows. And so the initial condition has to be over the first 2 rows so that I can compute the third. So I need to set, in addition to u0, I need to set u1. And I'm just going to set it to the same function. So to u0. And so what that means is that I'm holding that string in that position for 2 beats, 0, 1, and then I let it go. And so it's like saying that the initial velocity is 0 of the string. Now the iteration. So the iteration is going to be over time, which we index with k, and it's going to be in the range from 0 to k. That is from 0 to k minus 1, but you remember that the range is non-inclusive, so we say k. And now notice that we have already written the first 2 rows. So we actually don't want to start from the 0th row, we want to start from the 3rd row, which is index 2. So we're going to range from 2 to k. The next thing we have to do is to input the update equation. And so here it is, and here is my cheat sheet. I have copied it pretty literally, and I'm going to paste it in here. So it says that u at time k and some index I depends on the u's from previous time steps. Now, we haven't defined our I loop yet, so I is going to range as well, and we'll see what that is in a second. But I want you to notice that here I am squaring gamma in every loop. And that's a lot of wasted computation. So I'm going to define a new variable gamma 2, and that gamma 2 I will compute it in my dependent quantities area, so as gamma squared. So now I have this gamma 2. Okay, let's think about the for loop over I. We have this picture here. So this picture is showing that we are at a particular time k, and we have that the value at I is dependent on these 4 previous quantities that we saw. So we're going to, our for loop over I is going to sweep across a row and write in the values. Now, the 2 bars on the sides, the gray bars, those are the boundary conditions. So at index I is equal to 0, the value is already 0. We don't want to write there. We want to start writing at I is equal to 1, and we want to end at I is equal to I minus 2 because the next one is a boundary condition. So let's do that. Okay, so I is going to range from 1 to I minus 1, since we want to go to I minus 2. And now what remains is to set the boundary conditions. So u at every time, the first column should be equal to 0, and u at every time, the last column should be equal to 0. Okay, that is our iteration. That's our update equation. We have now computed the whole solution u, and we're done. But I want to show you a different way that preserves more of the vector structure and eliminates this internal for loop. So let's go back to the picture. Notice that the for loop over I wrote all of the values within this green rectangle. And so I can refer to this as u at time k with columns ranging from the second column, 1, up to, but not including the last column. So this is u of k from 1 to minus 1. Similarly, the previous row is u at k minus 1 from 1 to negative 1, and the second previous is uk minus 2 from 1 to negative 1. Okay, so also notice that when we wrote the ith value, that depended on the previous 2 time steps, the same I, and also the I previous and the I following. So in this rectangle or vector notation, those correspond to the one following would be an array going from the second value, but including the last value. And the one to the left would be a rectangle going from the first value to the second to last value, or the third to last value. Okay, so those are, this one is u of k minus 1 from 0, so I don't have to specify that, up to -2. And the one shifted to the right would be uk from 2 all the way to the end. All right, now let's use this notation to rewrite that inner loop. So the idea here is that we can replace this for loop, which executes scalar operations, with operations over the whole arrays, which are the rectangles. So let's do that. We remove the for loop, and now instead of assigning to the scalar uki, we are assigning to the array uk from, that's the green rectangle, from 1 to -1. And then now we have to replace each of the items on the right-hand side with its respective rectangle. So this one, uk minus 1i, that would be the red rectangle. So that goes from 1 to -1. uk minus 2i would be this dark blue rectangle, 1 to -1. Then gamma from, and then u from of k minus 1, I minus 1, so that's the shift to the left. That's the light blue rectangle. So that goes from 0 to -2. Then again the red one, so 1 to -1. And then the shift to the right, so that's the magenta rectangle, goes from 2 to the end. So we have essentially now the same code, but with one less loop. I would actually make this easier to read by defining these rectangles with their own notation. So I could call, say, uk minus 1 would be this one, the red rectangle. And that, oh, forgot a u, that appears here, and it appears also at the end, right here. And then, etc. uk minus 2 would be this one, the dark blue one, and then we have, etc. uk minus 1, I minus 1, uk I minus 1, k minus 1, I plus 1. So here you have the code right there. We've now arrived at the final piece, which is to create the animation. And here you see above me the animation that we want to create. So how are we going to do this? Well, to create an animation, you first create a figure, and then you capture that figure, then you change it a little bit, you update it, then you capture it again, then you update it again, you capture it again, so forth, until you have a sequence of frames, and those frames are saved to some movie file, like an MP4 or an animated GIF. So that's a lot to do, but Matplotlib has a single function that does it all for you, and that function is called funcAnimation, and it is part of the animation subpackage of Matplotlib. So we need to import that. We need to import matplotlib.animation, and we're going to give it the alias ANI. Okay, that's imported. Now I have this function called funcAnimation. That stands for function animation. So the function is this update function. What do we have to tell function animation? Well, we have to tell it what is the figure that it's going to be capturing. We have to tell it what is the function that is going to do the updates of the figure. We have to tell it how many frames to include in this animation, and we have to give it the interval in milliseconds between those frames. A couple of these we already know. So the number of frames, that's going to be our capital K. That's the number of time steps. And the interval between them is dt. But dt is in seconds, and interval has to be in milliseconds, so we just multiply this by 1,000. Okay, now we just have to give it the figure, and the update function. The figure, we are going to give it the very first frame. We're going to paint the first frame, this is what it looks like. And I have here a bit of cheat sheet code to do that. So I'm going to put that right above. Okay, this creates a figure and an axis, and then puts a plot, that's the blue line, with the first row of u, that's the initial condition, then creates this text element, places it at x is 0.7, y is 1, and this is the string and the font size, and sets the x limits and the y limits. Okay, that's our initial frame. We can take this figure handle or figure object and pass it into FuncAnimation. Now we just need to give it an update function. I'm going to call that update function update. And now I need to define it. Define update. Okay. The update function takes the frame number as input. That's just the same as in our case, the time step. And so we called that k. And now, within this update function, we need to modify all of the graphical elements that change between frames. And those are the line and the text. So in order to do that, we need to hold on to whatever these functions, plot and text, are returning. So we're going to just keep those as object lines and text. Now, the plot function returns a list of lines, and we only have one line, so that list only contains a single element. And so I'm just going to keep an object that is that single element, so the first element in lines. Now, okay, I can run this. Here's our initial frame, and we can see, if I look at this line object, that it has setters. These are functions that you can use to change the attributes of the line. In particular, we can change the y data. Okay, so that's going to change the height of the line, which is exactly what we want to do. So within the update function, we want to set the y data to the current row of the U matrix. Now what do we want to do with the text? What setters does that have? Well, you can set the value of the text itself. So let's do that. Let's set the value of the text, and we're going to set it to an f string that says time, and then it takes the current value of t and formats it point to f. Now, this is called an f string, and we're going to learn about this in our next module, so you don't need to worry about it. T is, as we know, dt times k. Okay, that's our update equation. Now we have everything that FuncAnimation needs. We just need to save whatever it produces. We're going to call this string movie. And to get this to work, we just need to do one more thing, which is to set the animation.html parameter of matplotlib to JS-HTML. We need to do that so that the player of the animation works correctly within Jupyter Lab. So I add that, then I call the string movie at the end of this cell so that it creates the player. And now I'm going to restart the kernel and run all. This is going to take a while, so I will fast forward. Okay, so here we have it. It created the player. We have play buttons. We can play it, pause it, go to the end, go to the beginning, and so forth, accelerate, reflect, do it once, do it in a loop. Many options here to play around. We can also save this movie to a GIF file using this save function and using the writer pillow. Now, there are other writers that you can use. You can also save to other formats. This is just one of the options that you have. Okay, then mission accomplished. We've created an animation using Matplotlib. I'll see you later. Bye.